Hey friends, this is a video for the differential equations class. It is an introduction to the basics of matrices. If you have already dealt with matrices and know how to do addition, subtraction, multiplication, and maybe inverting matrices and determinants, this video is not for you. This is kind of aimed at getting started on things like that. Okay, but in any case, I'm going to look at I'm going to look at several quick examples, and I apologize if my voice sounds a little bit weird, but sometimes that happens. So we're going to take a look at stuff here on the iPad. If it works, yay! It's going to work today. So matrix basics, yay! So if you take a look here, we have a matrix and a vector. The vector you can see is just 5, 6. I am super duper creative about how I create all of my examples. 1, 2, 3, 4, 5, 6. Wow, right? Yeah, anyway. So if somebody asks you what size this matrix is, you should respond that this is well, you should respond with thinner lines than that. You should say that that is a 2 by 2 matrix. It has 2 rows and 2 columns. All right. If this vector up here, if you were describing it as a matrix, then you would say that it is a 2 by 1 because it has 2 rows and 1 column. All right. Matrices are always going to be square. So you can always describe that I said square. They're always going to be rectangular, so you can always describe them in that sort of way, rows by columns. All right. So adding matrices together, the matrices you're adding have to be the same size. If they're different sizes and somebody asks you to add them, just say no, because it can't be done. It's not defined, okay? So then if you're multiplying matrices, then you have to look at what you're multiplying, the first one, and what you're multiplying the second one, right? And the number of columns on the first one has to match the number of rows on the second one. If it doesn't, you cannot multiply them, okay? If you say, oh, I want to do something different in order to make it work, fine, you're making up something. It's not math. So that sounded really hateful, but oh well. So what we're looking at here is how to multiply this matrix A times this vector X. And so I'm going to take this 1, 2, 3, 4 here and multiply it by this 5, 6, right? So I always visualize this as taking the vector that's coming on there at the end and tilting it up sideways and multiplying it by the columns of the matrix you've got there. That would be the reason why you have to have the same number of rows in the second one as you have columns in the first one. All right, so just take those entries, the 5 and 6, and multiply them by the vectors that are the columns. And of course you have 5, 15 plus 12, 24. And those are the same size, so you can add them and you get 17, 39. Okay, boom, that's what you're doing there. Okay. If you have dealt with matrices elsewhere, you may also have seen it done like this, where you determined since it was a 2 by 2 multiplied by a 2 by 1, that the result was going to be 2 by 1, and then you made the shape ahead of time, and then you said, I want to take the column vector here, the 5, 6, and dot it with each of the rows. So I dot it with 1, 2, and then I have 5 plus 12, and then I dot it with the 3, 4, and I have 15 plus 24, and I get the same result from doing that, okay? Either way you want to think of it is totally and completely fine. However, the advantage that you have with thinking about it this way is that a certain result that we're going to have in just a few more slides will make a little bit more sense. Okay, so it's just kind of saving a little bit of the thinking there. So, all right. So then we're going to take a look at another example here. And this is kind of illustrating that we can do this in more than one way. So first we're going to think about the by here, all right? And if you think about the way that I just talked about, that means that we're going to take the entries of y, 7, times the vectors of b, I'm sorry, the column vectors coming out of b, and that means that we will here have 7 plus 16, and we'll here have 21 plus 32, and then we'll have 35 plus 48. So we end up with, gosh, 23, 53, let's see, 70, 80, 83. Oh, it's weird, all the threes there. Okay. So that's doing the exact same sort of thing, just with something that's not square for the matrix that you start with. Now, on the other hand here, we can also take z, b, and pre-multiply there. So then you've got to think about with that, that you've got your 9, 0, 1, and that you're going to have the 1, 3, 5, 2, 4, 6. Okay, so you can think of it a couple of different ways. Again, one way to think about it is to think about you have a 1 by 3 times a 3 by 2. The 3's match up, and your result will be a 1 by 2. So if you think about it that way, that's one way to go at it. And so with respect to that, since we've got 1 row and 2 columns, then we have 2 entries to do. We'll take the 9, 0, 1, and we'll dot it with the 1, 3, 5. And when we do that, we get, for this first entry here, 9 plus 0 plus 5, so 14. And then take the 9, 0, 1 and the 2, 4, 6 and dot those. And so for this other entry here, we will have 18 plus 0 plus 6, so we end up with a 24. Okay, so yeah, that's one way to look at those. Another way to look at them is to say that you are going to think about this 901 as being 3 columns, and that you're taking the linear combination there with the 1, 3, 5 of that in order to get the first column, and then you end up with the 14. And then to get the second column, you take the linear combination of the columns 9, 0, 1 with the 2, 4, 6 as the coefficients, and you end up with the 24. Okay, so a couple of different ways to think about it, but multiplying matrices is more something to take a quick look at than anything else. All right. So here is one more example of that. Notice we have 3 rows, 2 columns, 2 rows, 3 columns. So that means that we can calculate AB, but we can also calculate BA, right? So if we're calculating the AB here, then we would match up the 2 and the 2, and we would know that the result we're supposed to get is a 3 by 3. So let me actually put a little bit more space in here. So yeah, I'm going to go ahead and say 1, 2, 3, 4, 5, 6 here. And I'm going to put the B here, the 7, 8, 9, 0, 1, 2. All right, and our result needs to be a 3 by 3. All right, so we're going to take column from the second one and dot it with a row from the first one in order to get our result. So 7, 0 dotted with 1, 2 gets us just the 7. Okay, and then I need to erase out the line that I just put in there. All right, and so now we're going to continue on, staying on the first row. I guess I didn't need to. We're going to dot that with the second column. So 1, 2 dotted with 8, 1. So 1 times 8 is 8, plus 1 times 2 is 2. So we get a 10 there. And then we'll stick with the same row, but go on to the third column. 9, 2 dotted with the 1, 2. So we get 9 plus 4 is 13. Okay. So then we'll move on to the second row. And that means we're going to get on into the second row in the result there. So 3, 4, dot it with 7, 0, and you'll get 21. And then dot it with 8, 1, and you'll get, let's see, 24 plus 4 is 28. And I guess it helps if I actually write it. All right. And then we move on and have 3, 4 being dotted with 9, 2. So 3 times 9 is 27, 2 times 4 is 8. So we'll multiply that, or we'll add that and get 35. All right. And then we move back to the first column, but we have to go to the third row. So we're taking the 5, 6 and dotting it with 7, 0, and we'll get 35. And then we take the 5, 6 and dot it with the 8, 1, and you'll get 40 plus 6, 46. Yuck. And then finally, we'll move to the third column here, and you'll have 5, 6 dotted with 9, 2. So you get 45 plus 12, so 57. Yeah, big numbers, right? All right. So that's dotting and getting the AB. So if you want to do BA instead, 7, 8, 9, 0, 1, 2, and then we dot with 1, 2, 3, 4, 5, 6. All right, since that is a 2 rows by 3 columns multiplied by 3 rows by 2 columns, the 3's will cancel, and we will get a 2 by 2 matrix. So with regard to that, we're going to start with this top row here, and we're going to dot it first of all with the first column. So 1 times 7 is 7, 3 times 8 is 24, and 9 times 5 is 45. So 76. Okay. And then we move on to the second column there. And so we have to dot 2, 4, 6 with 7, 8, 9. You get 2 times 7 is 14 plus, and 14 plus 4 times 8 is 32 plus 9 times 6 is 54. And so you end up with what? 86 plus 14, so 100. Right? And then we move back. Oh, no. We move back to this first column here, and we're no longer going to be in the first row, but rather the second row. Okay. And so we'll take the 0, 1, 2 and dot it with the 1, 3, 5 and have 0 plus 3 plus 10, so 13 there. And then we move over to the second column, and we dot that, and so we have a well, it would help if I did it right, wouldn't it? We have 0 times 2 is 0 plus 1 times 4 plus 2 times 6. So we end up with a 16 there. And then we have to put the little bracket on, and then we got it. Okay. So multiplying matrices is something that is non-commutative. AB and BA are not equal to each other. So one of the things you might question for this is, okay, what's matrix multiplication really got to do with anything? And this is where we're heading next here. So in this particular case, we're going to look at having this set of 3 vectors here and trying to determine whether we can get another vector as a linear combination of those 3 vectors. So is there a way to say A1 x1 plus A2 x2 plus A3 x3? And in order to figure that out, it helps to, actually have the honest to goodness vectors in there, right? So let me see if I can there's a neat trick with my little notes program here where I can copy it and put it down here. Okay, so apparently it's not happy with me right now because I didn't do it exactly right. I told it to copy, and then I want it to paste. I will try this one more time, and then I will just write the damn thing. Copy. Paste. There we go. All right. And then copy, paste. All right. copy, paste. All right, so, so if you're taking a look at that, you could see that we could think about that as having the A1 plus 4A2 plus 7A3 equal to 1, and so forth down the line. And I hit the wrong thing there. A1 plus 5A2 plus 8A3 equals 1. And what's the last one? 3A1 plus 6A2 plus 8A3 equal to 1. So that would be like a system of equations. And if you know about solving systems of equations, if in the 2x2 case, yes, go do substitution, blah, blah, whatever. But once you get to the 3x3 case, if you all you know how to do is substitution, you're really going to kill yourself working on this. So we don't want to handle it that way. I think on the next page, yes, on the next page, I have something to show you how to do your solutions of systems in a nice way. Okay, so one of the things that you learn to do with systems of equations is to take and add equations and multiples of equations to each other in trying to eliminate variables. And so what we're going to do here is that I'm going to take on row 2, I'm going to subtract 2 times row 1 and put the result back into row 2. Okay, so I'm just going to write down here what happens with this. I'll leave the 147 and the 1 across the top. Okay, so when I do that, I will have 1 minus 2 is 0, 5 minus 2 times 4, so 5 minus 8 is negative 3, and then 8 minus 2 times 7, so 8 minus 14 is negative 6, and 1 minus 2 is going to be negative 1. Okay, so that's the first thing I did. Then for row 3, I'm going to subtract 3 times row 1 and put that back into row 3. Okay, so the first thing here, you get a 0. That's my goal. I am clearing out everything that's under the first entry there. The next go round, I'm going to try to clear out everything that's under the second. So, all right, so what was I doing? Oh yeah, 6 minus 3 times 4. Well, that's 6 minus 12, so that's a negative 6. And then 9 minus 3 times 7, so that's 9 minus 12 is negative, I'm sorry, 9 minus 21 is negative 12. And then 1 minus 3 is negative 2. Okay, so I am going to tidy up here a little bit, and I am going to say a negative 1/3 of row 2 goes back into row 2. And negative 1/6 of row 3 goes back into row 3. All right, we didn't really have to do that, but it's just keeping things tidy so that the next step is easy. All right, and so 0, 1, 2, and 1/3. And then 0, what? 1, 2, and 1/3. Goodness. All right. So now you could go ahead and say here that you're going to take row 3 and just subtract row 2 from it and put that back into row 3 so that you have 1, 4, 7, 1, 1/3, 0, 1, 2, 0, 0, 0. Okay. Now, at this point, you actually have enough that you can figure out our final answer here and stuff. Okay, that we actually have several different ways to get our final answer. We can at this point back substitute and figure out stuff, or we can continue this process where we cleared out stuff under the first pivot and under the second pivot, and then we can go back and clear out stuff that's above the first pivot by subtracting 4 times there. Of course, the bottom row is going to stay zeros forever. Okay, and I'm going to have to subtract 4 times the second row from the first row. So 1, 0, let's see, 7 minus 4 times 2 is -1, and 1 minus 4 times 1/3 is -1/3. Okay, so what this tells me is that A1 minus A3 needs to be -1/3, and that A2 minus 2A3 needs to be +1/3. I have a system of 2 equations but 3 unknowns. That means I'm allowed to choose one of them. What am I going to choose for A3? What's the easiest thing to choose? It's A3 equals 0. Okay, and then that says that the A1 needs to be -1/3, and the A2 needs to be +1/3. So coming back to the problem we were actually working on here, and let me erase these quicker instead of, and so now I said A1 needed to be -1/3, I think, and A2 needed to be +1/3, and A3 needs to be 0. Okay, so that says we can express 1, 1, 1 as a linear combination of those 3 vectors there. But it's going to turn out that if we try to do that for this other one down here, that we won't actually be able to do that. And push that off to the side and erase out the solution that we got there. So A1, A2, A3. So like before, we're going to get a system to try to do this. And I hope that I wrote that down 2 pages hence. Why, look, I did. And we're going to try to do the same process as before in trying to solve this. Now, because it's the same process as before, it really depended mostly on the coefficients that we were getting in the left-hand part of it. It should be something that's pretty straightforward to do. So what was it? We took and subtracted 2 times that from the second row. So we get a 0 here, a -3, a -6, and let's see, 2 minus 2 times -1. So 2 plus 2 is 4. Okay, and then we subtract 3 times on the bottom row, and for that we get a 0 and 6 minus 3 times 4, so -6, 7, I'm sorry, 9 minus 3 times, so -12, and then 1 minus 3 times -1, so 1 plus 3 is 4. Okay, and so then we're going to tidy up here and have 0, 1, 2, and 4/3, 0, 1, 2, and sorry, that was supposed to be a negative 4/3, wasn't it? Yeah. And so then here we'll have a negative 2/3. And when we do the next step, if you didn't already spot that we're in trouble, you will spot it on the next one, because when we subtract that off there, we're going to have 0, 0, 0, and we're going to end up with a 2/3. So that bottom row says that A1, I'm sorry, 0A1, 0A2, and 0A3 all added together needs to be 2/3. That is bad. There's no way we can multiply things by 0 and get anything other than 0. So in fact, this problem over here has no solution. Okay, so some problems like this we can solve, and some problems like this we can't solve. And so the question is, how do we tell whether we can solve it or not? So the basic way that you can check is to calculate the determinant of that. And so here in a minute, we're going to look at doing something else where you would calculate a determinant. But for 2x2 matrices, calculating a determinant is simply that you calculate across there. Yeah, I'm sorry. There needed to be another example in here to show this, but so for a 2x2 matrix, this can only be done with square matrices. But for a 2x2, you multiply the main diagonal, 1 times 4, minus the transverse diagonal. That's the 2 times 3. So 4 minus 6 is negative 2. If the number you get is 0, then it is not always going to be possible to solve one of those. Okay, there will be some solutions out there, or some vectors that you cannot represent as a linear combination. If the number you get is not 0, then it's totally going to be possible to solve any of these problems. Okay, and one of the things that we talk about on that is, if you want to say that you can get a solution to AX equals B, the way you tackle it is to get a matrix that's called the inverse of A and multiply it on both sides there. These will cancel and you get A inverse B. Now, if you said, oh, no, I'm not going to do that, I'm going to divide, then you're just wrong, okay? There is no matrix division. There's matrix multiplication, and some matrices you can get the inverse, not all of them. So if you're needing to solve one of these problems, it has to have an inverse before you can do it. So, and it has to be something you multiply on the left. Remember, matrix multiplication was not commutative. So that process that I'm referring to of getting the inverse matrix is simulated by that same Gaussian elimination technique that we did just a minute ago of solving. What we effectively do is to come along here and put 1, 0 and 0, 1. If you had larger matrices you were talking about, you'd have to do 1, 0, 0, 0, 1, 0, and 0, 0, 1, or however many you needed. It's the identity matrix of that square size. But the reason for that is that those vectors form what's referred to as a basis for Rn, for whatever size of vectors that you're living with. And so because you can always find some linear combination of those two vectors, or 3 or 4, however many you're working with, since you can always find a linear combination of those, then if you can find a linear combination of these columns here that give you each of those columns, then you can go ahead and find a solution for anything. And really that solution setup has to do with the whole, how we get an inverse, okay? So we are going to go ahead and tackle that here. And the notion that we really have is that putting that, that identity matrix over there on the right-hand side and going through the process of turning the left-hand side into the identity matrix will record the appropriate actions on the right-hand side in order to undo the matrix that we're dealing with. So I am skipping over huge amounts of theory here, I'm sorry, but what we're going to do here is to take and leave the first row alone, and we're going to subtract 3 times the second row to clear out under the pivot. So 0, -2, -3, and still 1, okay? And then we're going to divide out that -2 and have that. And I'll go ahead and copy this down. You could skip a step here if you can do the visualization. But then I'm going to take and subtract 2 times the bottom row from the top row. So it doesn't do anything to that 1, but it makes a 0 there. And let's see, I said subtract 2 times the bottom row. So I'm subtracting 3 from 1, so I get a -2. And I'm subtracting -1, so adding 1 to 0, and getting 1. All right. So if you've got the vector, the matrix A being your original 1, 2, 3, 4, then the matrix A inverse is going to be -2, 1, 3, 2, and -1/2. As long as I copied all of my numbers down there, you should find that if you multiply A times A inverse or A inverse times A, that you should get the identity matrix out of them, okay? I will leave that to y'all to actually do the confirmation of. All right. So let's do another one, and it's a 3x3, okay? Now, before we tackle it, let me show you how to get a 3x3 determinant so that we don't waste our time trying to invert something that can't be inverted, all right? So if you want to take a matrix and get its determinant, and it's larger than 2x2, choose the first row. You could also choose the first column, and maybe I copy this down here. And we're going to pull out the, we're going to pull out that first row, 0, 1, 1. And in actuality, I didn't need to leave that much room there. Okay. And they alternate in sign. So the 0 that's in the upper left-hand column is going to be a plus, and then a minus, and then a plus, okay? And for that 0, we're going to take and cross out the row and the column that the 0 is in, and the smaller matrix there we're going to copy down, okay? So that's 0, 0, 0, 1. So 0, 0, 0, 1. Minus 1 times, now that 1 was here, so we're going to cross that out, and now we're going to have 2001. So 2001. And then the last one is in this row in this column, so it's going to have 2000. So we'll have 0 times. Now we've got 2 by 2s. 0 times 1 is 0, minus 0, minus 1 times 2 minus 0, plus 1 times 0 minus 0. So we end up with a -2 here, okay? So that -2 is not 0. Therefore, when we try to invert this, we will not be wasting our time. So all that stuff there was just to the side to make sure that we could actually find this inverse. What was it? 0, 1, 1, 2, 0, 0. Okay. So we're going to come along here. And it would be super convenient if we had something that was not 0 in the upper left-hand corner. So we're just going to swap 2 rows. And that is totally legal to do. And 1, 0, 0, 0, 0, 1, 0, 1. Okay. And now on that top row, we need to multiply it by 1/2. And that's no problem. Then this bottom row, we're not really going to have to do anything with it. So I'm just going to copy it down. And now we need to subtract the bottom row from the second row in order to clear out that point there. That's that 1 that's there. So we'll have 0, 1, 0. But now we have to take 1 minus 0 is 1, and 0 minus 0 is 0, and 0 minus 1 is, sorry, is -1. So now if our matrix A were 0, 1, 1, 2, 0, 0, 0, 0, 1, then the appropriate inverse for that would be 0, 1/2, 0, 1, 0, -1, 0, 0, 1. Boom. Okay. So you can only invert a matrix if its determinant is non-zero, but the process for inverting it is this Gaussian elimination sort of thing, unless you have a computer to do it for you. So, and those are all the ones that I have to show you there. Now let me jump across here and find my quick little Python demo here, and I will link this to y'all so that you can see what's going on with it. But what we have here is that in Google Colab, the Python code, in order to write a matrix, is that you have to tell it that you want an array, and then the array is going to have a row listed as bracket number, you know, with commas separating them. And then in order to get a matrix out of that, then you're going to make the rows have entries, or the rows into entries in a bigger row, okay? And so when it wants to actually print these out, when you tell it to print something, it will print them out with one row and then the next row and so forth, so that you can read them fairly easily, okay? One bad thing that we have here is that NumPy does not have matrix multiplication defined with a multiplication operator. It instead has it as a function. This is also true in Java, and this is a real detriment to numerical computing. So I'll make reference to a way around this here in a minute, but for right now, if you want to multiply two matrices, you have to define them, and you have to say matmul. And in order to get matmul to work, you have to have imported it, okay? I make a quick note that I do these one function at a time so that you can read them. If you don't want to have to type all that crap out, you could just say from numpy import star, or just, I think maybe import numpy. In any case, though, the addition operator works the way you'd expect it to. If you try to use the matrix multiplication operator, it will give you the wrong answer. So, and it will not warn you about it because that's not what computers do. All right, so then from the SciPy linear algebra package, we get to the function for determinants and for inverses. And we inverted 1, 2, 3, 4 earlier, and I hope I'm getting the same answer here. But what I have to do is to tell it 1, 2, 3, 4 is my matrix, and then I tell it to calculate the determinant of that matrix and to calculate the inverse of that matrix, okay? And so, yeah. And so you can see printed out down here, and I should have had this inverse of A. I should have told it to print a blank line after it so that it would be easier to read. Okay, anyway though, so when you say the inverse in INV of A, if that is something that can be done, it will calculate it for you. And I hope that that is the result that we got earlier. If it's not, it's like me copying something down wrong. However, notice here that I chose a V that has 1, 2, 1, 2. So the rows are the same vector, and that's going to tell you that you're going to have something that's linear combinations of each other. And so consequently, the determinant is going to turn out to be 0, as we see down here. But when I asked it to calculate the inverse of B, because the determinant's 0, it can't calculate the inverse of B, so it gives me an error, right? Please remember that when a computer gives you an error, that's not like the worst thing that can ever happen. It's just informing you something wasn't typed right, and you just have to go fix it, okay? But I purposely got an error there to show you what crops up if you try to take an inverse of something that's not invertible. All right, so then on the other hand, if you wanted to solve that 1, 2, 3, 4 equals 1, 2 here, you need to have your B be a column vector, not a row vector. And so you need to have its entries be here with a vector inside of a vector, an array inside of an array, I mean. If you don't, NumPy will try to solve it for you, and it will give you the correct answer, and it kind of hurts my soul a little bit that it will give you the correct answer, because it should just give you an error, because at some point it's going to cause a problem that it solves things for you. So, all right. A couple more quick things here. For the brave of heart, there is something that's called SymPy. And SymPy tries to do symbolic manipulations. This is what we refer to as a computer algebra system. And it can do some things of solving equations for you. So if you've got linear equations to solve, you can use this function called linsolve, as long as you import it. And as long as you go ahead and tell it that these things here, X, Y, and Z, are symbols called X, Y, and Z, then it's going to be okay with them. If you try to use X, Y, and Z and tell it to solve for things without telling it it's a symbol first, it will complain and say things like, oh, but x is equal to 7. And yeah, so anyway, you have to tell it things are symbols, and then you can use it to do this linear solving. You can also get it to do your algebra of like multiplying out polynomials and factoring stuff. It is pretty slick, but unfortunately not everything carries across. So if we're talking about matrices, and you say something about, I want to do matrix multiplication with a and x and subtract b, and you know that the sizes should work out and everything, it will say, nope, nope, the input operator 1. And I do not know how it got 1 out of that. So, but it is interesting that SymPy has this object called matrix, and you can take in matrix and create objects that are the appropriate sizes, and it will actually multiply them for you. So, so here I went ahead and created something where I had a column, I had a row vector, and I also had a column vector. And if you remember from the example we did earlier, you should be able to pre-multiply maybe by a 1/2, but you should not be able to post-multiply by this p here that I've made up. However, SymPy will try to do it anyway, and it gives you the exact same looking results. Unfortunately, their matrix does not have a printout that prints nicely. There is a way around that, but you can tell it to print using LaTeX and something called MathJax. I can't make it work on Colab though. If you are instead using your Python through Anaconda or Jupyter or something, you can probably get that to work, and you can get much nicer looking results where you can read them better. But Colab is free, and it's accessible to everybody, and it's easy for you to share things with me. So that's the reason why we're using that. All right, so you have an assignment that has you doing some simple matrix multiplication and solving some things, and I've provided you with enough resources that you should be able to check all your work. So I need everybody to get 10 out of 10 on this assignment. All right, so see you in class.